model of the MOSFET. So what we're going to do is we're going to be modeling the MOSFET as a two-port network. The same thing that we did for the bipolar junction transistor. So if this is our MOSFET, can we find an equivalent two-port network, okay, that can replace the MOSFET? So we're only talking about the MOSFET here. No other external components, just the MOSFET. For us to be able to convert the MOSFET into a two-port network, we must linearize the transistor, such as what we did for the BJT. We must linearize the transistor. And you can only linearize the transistor if the variation in the input is very small. Because it is only when you have small input variations where your transistor characteristics can be approximated by linear components. Remember that the MOSFET characteristics are nonlinear, they are exponential. The relationship between voltage and current is a function of a quantity that is squared, diba? VGS minus VTH squared, which is not linear, that is exponential. So when your relationship between voltage and current is not linear, you cannot use the tools that you apply for linear circuit analysis. But now, because we linearize the MOSFET, you can use the tools that we apply for linear circuit analysis. So what are these tools? Okay, the superposition, what else? Nodal analysis, mesh analysis, all of those tools, no? Thevenin equivalent, Norton equivalent, circuit simplification, all of that. Okay, and then just like the BJT, we will employ a unilateral model. So we're saying that the input affects the output. So the quantities here will affect the quantities at the output, but the output does not affect the input. Yung mga quantities dito will not affect the input. Actually, this model has limitations because in some configurations, in some topologies, the output will affect the input. But for the meantime, we will just assume a unilateral model. The case where the output affects the inputs, you're going to take that up in higher EE courses when you have what we call feedback. So the transistor is a two-port network. Just like the BJT, our independent variables are your input and output voltage. So your input and output voltage, those are our independent variables. And then your dependent variables are your input and output currents. So you have your two dependent variables expressed in terms of your independent variables. So I1 will be a function of supposedly VI and VO, pero dahil unilateral, yung input current is not dependent on VO dahil nga unilateral. Remember what we said, unilateral, the output should not affect the input. But I sub O is a function of both VI and VO. So I sub O is dependent on both VI and V sub O. So let's begin our linearization. So what we're going to use in our process is the NMOS common source topology. NMOS common source topology, where our source is the common terminal between our input and our output. Take note, because we are dealing with a small signal model, what we are dealing with are going to be the variations in the input and the variations in the output. So pag tinignan nyo yung subscripts natin, our subscripts are the lowercase letters. We are not dealing with VGS, no? We are dealing with V small g small s. So we're only dealing with the time varying component of your input signal. Okay, so this is our large signal model relating ID and VGS and VDS. Naalala niyo itong term na to? What does that take into account? Yung 1 plus lambda VDS? You remember what that takes into account? Kasi dati-dati yung model natin, wala nitong term na to, no? Wala nitong term na to. But now we added a term. What does that take into account? Okay. Anyone? Okay, that takes into account yung channel length modulation. Channel length modulation. Kasi habang lumalaki yung value nung drain to source voltage, umiikli yung channel natin, no? The pinch off area goes closer to the source. So mas malaki yung pinched off area. And because of that, our current tends to be higher. So that's channel length modulation. That is what this takes into consideration. So if I plot this equation, plot ko lang to, assuming that the value of VDS is a constant, in other words, I make a plot of this equation for a particular value of VDS, okay, I'm going to get this curve. Okay, the other assumption of this curve is that VGS is greater than VTH. In other words, your transistor is conducting. Kasi kung hindi natin gawing VGS is greater than VTH, actually this curve is going to be negative at some point, no? Sorry, it's going to be translated at some point, no? In other words, hindi magiging zero yung current pag VGS is not greater than VTH, no? So anyway, so this is the curve of this equation. Okay, and we mark in this curve our quiescent point, no? So the Q point, so you have a quiescent point for VGS and a quiescent point for I sub D. For small changes in VGS, take note, no? VGS is capital G, capital S. So that means kasama dito yung bias voltage. Remember? Pag capital G, capital S, kasama yung bias voltage. For small changes in VGS, the slope of the transfer characteristic curve in the vicinity of the Q point can be considered constant. So how do I illustrate that? This is a small change in VGS. Ito, that's a small change in VGS. If I take a look at the blue line and I take a look at the red line, in between or in this range, you can approximate the blue line and the red line, okay, to be the same. Yun ang sinasabi ko rito. For small changes in VGS, yung blue line and the red line will be the same. And that will result in this change in I sub D. Ito yung magiging change in I sub D. Pag yung value ng VGS is here, ito yung I sub D. Pag yung value ng VGS is here, ito yung I sub D. So ito yung change in I sub D. In other words, this is actually I small d. That's I small d. And this is actually V small g small s. Okay. Now what is the slope? What is the slope of the red line? The slope of the red line is actually the slope of a straight line that is tangent to the curve at the Q point. If I take the slope, if I take the derivative of the blue line at the Q point, that is the slope of this red line, no? The slope at the tangent of the curve at the Q point. So that for small changes in VGS, I can approximate my change in ID to be equal to the slope multiplied by VGS. Because slope is change in ID with respect to VGS. No? So for a small change in VGS, I can get now the change in I sub D. No? Where, again, no? V small g small s is the change in V capital G capital S, and I small d is the change in I capital D. You have to be very strict with your subscripts, no? Because your subscripts say a lot about the quantity. And that is what we define as the transconductance, the slope. So it's exactly the same thing that we did with the BJT. You remember the BJT, the transconductance is partial of ice of C with respect to VBE. Dito ngayon, it's partial of ice of D with respect to VGS. Okay, so let's try to derive the transconductance. So what is ice of D? We said that ice of D is equal to 1/2 K. Okay, now I'm going to distinguish between N and P. No? So Kn, just to distinguish it as an NMOS transistor, okay, this is VGS minus VTH squared 1 plus lambda VDS. This is large signal. Kaya yung mga subscripts ko are all capital. Okay, I get the partial of ice of D with respect to ito, no? With respect to VGS. Okay, what is that? These are constants. Constant ito. This is a constant. No? That's why partial, no? This is a constant, this is a constant. So labas yan sa derivative. So kukunin ko lang yung derivative nitong quantity to. What is the derivative of this? VGS minus VTH squared. I heard it. Ano yun? Okay, 2 VGS minus VTH. So I have 1/2 Kn 2 VGS minus VTH, then 1 plus lambda VDS. Okay, and I evaluate this. This has to be evaluated at my Q point. We're evaluating that at this point, at the Q point, because I need the tangent, no, the tangent line at that Q point. Okay, so if I simplify this, now this is now my GM. Okay, this is just Kn VGS minus VTH 1 plus lambda, at the Q point, no, sorry. So this is VGSQ. Let me, para malinaw. Okay, this is Kn. So evaluating this as at the Q point, this is Kn, okay, VGSQ, okay, minus VTH 1 plus lambda VDSQ. Okay. So from here you can already get, if I know, no, kung alam ko yung quiescent gate to source voltage ko, at saka alam ko yung quiescent drain to source voltage ko, I can already get my transconductance. So this is one way of getting your transconductance. Okay, let's look for other forms of your transconductance. What will happen if so ito na yung isa, no? This is already one, no? What will happen if I multiply this by, let me multiply this by 2 VGS minus VTH, VGSQ minus VTH, over 2 VGSQ minus VTH. So I multiply it by 1 essentially. If you take a look at this, if you take a look at this now, ito. What is this? What is this that I'm encircling in red? Do you recognize that quantity? Ah, sorry. Mali. Ito pala. this one. Ito, no? Linawin ko lang, ah. Okay, this is multiplied by 2 VGSQ minus VTH over 2 VGSQ minus VTH. No? So I multiply it by 1. Now what is this quantity? This one, this one. Mali pa rin. Mali pa rin. Pasensya na. Hindi kasama yung ito. Hindi kasama to. Hindi kasama to. Hindi kasama to. What is that quantity? It's IDQ, di ba? No? Notice this is 1/2 Kn VGS minus VTH squared multiplied by 1 plus lambda VDSQ. Right? So that's IDQ. I'm glad you recognized it. So this is now going to be, so ano yung natitira? Meron tayong 2 dito, meron tayong VGS minus VTH dito sa baba. Okay. So this is going to be 2 IDQ over VGSQ minus VTH. So that is your other form. Okay. Meron pa isang form. No? So, remember, itong form na to, I can use this if I know VGSQ and I know VDSQ. I can get G sub M. No? Itong form na to, I can use this if I know IDQ and I know VGSQ. Okay, yung isa pang form, no? If I know IDQ and VDSQ. So any 2 of the 3 quantities. No? How do I get the other form? Okay, starting from here, I can compute for VGS minus VTH. No? From here, VGS minus VTH is equal to, okay, if I manipulate this equation, that's going to be equal to the square root of, kasi may square dito, no? So it's going to be the square root of 2 ID, no, over Kn 1 plus lambda VDS. Right? So just manipulating this equation. Okay, and I can substitute this now here. Ito pwede ko i-substitute dito. So I can get a third expression for G sub M. No? My G sub M is going to be the square root of 2. 2, dali lang. Okay, it's going to be the square root of 2 Kn IDQ 1 plus lambda VDSQ. So 3 possible expressions for G sub M. Yung una ito, where G sub M depends on VGSQ and VDSQ. Yung pangalawa ito, where G sub M is in terms of IDQ and VGSQ. And finally, this expression, okay, where G sub M is expressed in terms of IDQ and VDSQ. 3 possible expressions. But actually, you just have to remember one, and then you can derive the other from that one, ano? Just knowing this expression, you can derive the other. Siguro pinakamadaling tandaan ito. 2 IDQ over VGSQ minus VTH. So that's your transconductance. Okay, let's consider now output conductance. Transconductance describes the change in I's of D when there is a small change in VGS. Now, output conductance describes the change in I's of D when there is a small change in VDS. When there is a small change in VDS, no? So for the small change in VDS, what is your change in I's of D? Okay, if you remember your curve, no? This is your I's of D. This is your VDS. What do your curves look like? With VGS as a parameter, your curves look something like that. Okay, your curves look something like that. So you have a Q point somewhere. Sabihin natin this is your Q point. This is a VDSQ. So yung sinasabi nating slope, meron kang slope dito. Right? So that for small changes in VDS, makukuha mo yung corresponding change in IDS. No? So this is a slope because of channel length, channel length modulation. May slope itong curve na to. Okay? Yun yung dinidescribe ng 1 plus lambda VDS. For a small change in VDS, you have a small change in I's of D. That will be described by that slope. And that slope is this, no? The partial of I's of D with respect to VDS. Ito yung slope na yun, no? And this is what we call our output conductance. So all we have to do is get the derivative of I's of D with respect to VDS. So we consider this to be a constant. So what does that derivative come out to? Ano yung magiging derivative niyan? So G sub O okay is okay, ano yung derivative? This is a constant, no? This ends up being a constant, right? So this is just 1/2 Kn VGS minus VTH squared. Okay, what is the derivative of this with respect to VDS? Ito na lang yung kukunin natin yung derivative with respect to VDS. So what is that? Anyone? Lambda. Just lambda. So yun yung value ng G sub O. Okay, what will I do? Let me multiply this by, I'll multiply this by 1 plus lambda VDS over 1 plus lambda VDS. Again, no? What is this now? Ito combined with this. That's now IDQ. Right? If I get this combined with this, that's IDQ. So what is my G sub O? My G sub O is lambda ID, well, evaluated at the Q point, no? Evaluated at the Q point. Lambda IDQ over 1 plus lambda VDSQ. That is now your output conductance, G sub O. Okay. What is your output resistance? Your output resistance is just the reciprocal of your output conductance. So now it's 1 plus lambda VDSQ over lambda IDQ. So reciprocal nito. That is your output resistance. And note that for small lambda, this is negligible. For small lambda. So you just get 1 over lambda IDQ. pag sinabing lambda is negligible, ito yung formula mo for your output resistance. The final parameter that we want is our input resistance. No? If I go back several slides, ito, no? We want our input characteristics. How do we relate your input current to your input voltage? In other words, for an input voltage, what is my input current? And since this is linear, what we'll model that is a resistor. Kasi it's just a voltage as a function of current and linear. So what we'll model that is a resistor. But what is the input resistance of your MOS? For DC and for low frequency, for sa DC or low frequency, the input resistance is infinite. Because your gate is a capacitor. No? And for DC and low frequency, no, the impedance of your capacitor is very, very large. In fact, for DC, omega equal to 0, the impedance of your capacitor is infinite. Infinite means open circuit. So your input resistance is actually infinite. Okay, so putting that all together, what is my change in ID due to small changes in both VGS and VDS? So let's say I have small changes in both VGS and VDS. The total change in ID will be my transconductance multiplied by my change in VGS plus 1 over my output resistance multiplied by my change in VDS. And if you take a look at this looks like a nodal equation. Where this is one branch and this is another branch. So if you consider this to be the node, ito yung node na yon. Okay, what is ID? So one branch is this. It's a voltage-controlled current source, GM VGS, yung isang branch. Yung isang branch naman is a resistor. Yung output resistance natin. The current that will flow through here is VDS divided by R sub O, which is this term. Yan yung current na magfo-flow dito sa baba. Yung current naman dito is just GM VGS, no? Your voltage-controlled current source. And then what is the value of IG? 0. So this is what's nice about analyzing MOS transistors kasi wala kang i-analyze na circuit sa input side. At least low frequency at saka sa DC. Dito lang sa output side meron kang i-analyze. Of course, you still have to evaluate VGS. So here I gave you the expressions for G's of M and R's of O. Okay. So I mentioned that there are 3 possible expressions for G's of M, so this is just one of them. Okay. And then, if lambda is neglected, nagiging simplified yung mga expressions natin. If lambda is neglected, matatanggal tong term na to, matatanggal din tong term to. Any questions so far? So this is now your model. So this is your NMOS small signal model at low frequency. The model is linear. You've seen circuits like this in EEE 123. So you should not be scared. Pag may nakita kang circuit na ganito, dapat hindi kayo matatakot kasi dapat nahasa na kayong mag-analyze ng mga circuits na ganyan sa EEE 123. This will describe the response of the NMOS transistor to small signal input changes around the quiescent point. The parameters, what are your parameters? G's of M and R's of O are dependent on the Q point. So para mo para mo ma-determine itong G's of M at saka R's of O, wala kang choice. You have to compute for your quiescent voltages or your quiescent currents. Wala kang choice. And that's why at the start of this module, we tried to get you used to doing all sorts of DC computations sa mga transistors, di ba? Yung mga bias point computations. Hinasa na namin kayo doing all of that because you cannot avoid not computing for that because that is what G's of M and R's of O will depend upon. And remember, this is a unilateral model. So the output does not affect the input. And I want to mention that your NMOS and your PMOS transistors have identical models. And I think I illustrated that for the BJT, but let me go through that again for the MOS transistor. Ano yung magiging model natin ng PMOS? Okay? Ang magiging model natin ng PMOS, okay, you have your source at the top. Usually your source is drawn at the top, di ba? Pag dinodrawing natin yung PMOS, yung source nilalagay natin sa taas. Okay. At the input, okay, this is your gate, so this is your source. This is your gate. Instead of VGS, what do we have? We have VSG, right? Plus or minus VSG. Small signal, kaya small subscript. And then from your source, okay, you have a controlled current source here, and this is going to be GM, okay, VSG. And then here I have R's of O. So this is my source, this is my drain, and here I have VSD. That is my PMOS small signal model. Remember in PMOS, ini-invert natin yung mga subscripts. Imbis na VGS, VSG, imbis na VDS, VSD. Okay, anong gagawin ko ngayon? I'm going to flip this so that S is below and then G and D are above. So if i-flip ko lang. So dito ko lalagay yung S ko. Okay, and then here I will put G. So this voltage is plus minus VSG. But then, that is equivalent to plus minus VGS. Right? Kung dito, plus minus VSG, pag ginawa kong positive yung taas, babalik na rin ko lang yung subscript. So this is now plus minus VGS. Okay, my current source is pointing upward. Okay. So this is GM VSG, which is equal to G minus GM VGS. If this is GM VSG, that is equal to minus GM VGS. Kasi binaliktad ko yung subscript rito. Okay. And then I have my resistor here, R's of O. So this is plus minus VSD, which, sorry, baliktad mo. It's a plus minus VSD, okay, which we can write as plus minus VDS. So how do I get rid of this negative sign here? Baliktarin ko lang yung direction nitong arrow na to. So finally, what will my model look like? I have my gate, I have my source. Okay, so this is VGS. Okay. I want to get rid of the negative sign, so uh, I change the direction of the arrow. So this is now GM VGS. Okay. This is Rs of O, and then this is VDS. So parang magic. All of a sudden now this looks exactly the same as this. So the NMOS and the PMOS transistors have identical models. Okay, so that's actually all that I wanted to discuss for today. So what I was planning to do for the rest of the session, and this is also a request of some of the people attending the face-to-face session to have more problem solving, I decided to make you do this seat work. No? So this is an exercise. I want you to use the small signal model of the transistor to estimate the change in V sub O if V sub I increases by 20 millivolts. So here is my transistor. So this is a PMOS. And here are all the parameters. VDD 10 volts, RD 5K, case of P, kasi PMOS siya, 0.5 mA per volt squared, VTH minus 1, and lambda equal to 0.1. Okay, so first part of the problem is to determine, no? So step 1, determine IDQ, okay, VSGQ, and VSDQ. So this is VSG, and this is VSD. And then this is ISO D. So parang practice na rin nyo for the exam. I'll give you what, 10 minutes to do this. And if any of you have an answer, you can come to me and I can tell you whether your answer is correct or not. So ganun na lang gawin natin. So please try. So itong part na to, review yan for your exam because it was still covered in module 2. Computing for the voltages and currents pag DC. If anyone has an answer, you can come here to me and I can tell you whether your answer is correct or not. And I can also look at your solution if something's wrong with it and tell you what's wrong with it. Okay, somebody already got the right answers. Anyone else? So got the right answers. You can continue, no? Continue on the letter A and well, yeah, letter A and letter B. Actually, yeah. Yeah. I'll give people figure another 5 minutes, no? And then let's just do it together para makita niyo yung solution. Any last attempts from anyone? Okay, let's just do it, no? Gawin na lang natin. Okay, so ano yung VSG, no? VSG is equal to VDD minus V sub I, right? And VSD is equal to VDD minus V sub O. Sorry, not V. Okay, so from here, V sub O is equal to VDD minus VSD. Okay, your formula for, let's assume saturation. By the way, no, remember to always check your assumption. That's a mistake that a lot of students often make. They right away assume saturation, they come up with values, tapos nakakalimutan nilang i-validate yung assumption nila, no? So please don't make that mistake. Always validate your assumption because baka mali, ano? In which case you're not going to be using the correct formulas. Okay, so let's assume as saturation. So our formula for I sub D, pag saturated, is equal to 1/2 K sub P, okay, VSG minus the absolute value of VTH squared. And then this is where some of you made a mistake. Dapat meron nito, no? Because lambda was given as 0.1, and 0.1 is definitely not negligible compared to 1. No? So you have to have this 1 plus lambda, then you have to have your VSD. No? VSD. Okay. So what is this? No? This is 1/2. Case of P is 0.5. Okay. VSG is VDD minus VI. VDD is 10. VI is equal to 7.2. So VSG is going to be 2.8. So this is 10 minus 7.2. So this is actually 2.8 volts. Okay, 2.8 minus the absolute value of VTH. This is going to be 1.8 squared. Okay, 1 plus 0.1 times VSD. That's ID. But ID is also equal to V sub O over RD. ID is V sub O over RD. But V sub O is VDD minus VSD. So ID is also equal to 10 minus VSD all over 5K. So you have these two equations that you can equate. How many of you reached this point? Yung dalawang equations na pwede nyo equate. Okay, that's good to hear. No? So actually, madali lang. No? This is not, when you equate this is not quadratic. It ends up being a simple linear equation. Ano yung lumalabas? No? You have 10 minus VSD over 5 is equal to 1 half, 0.5, 1.8 squared, 1 plus 0.1 VSD. And if you compute this, you're going to get VSD is equal to 4.235 volts. Okay. So how many got 4.235 volts? 4.23 is okay, no? For actually 4.234 something, no? Okay. Dapat umabot kayo dyan. So VSD, this is VSDQ, right? That is your quiescent source to drain voltage. Okay, I can compute for IDQ. Okay, that's just 10 minus VSDQ all over 5, okay? And this will give me 1.153 milliamperes. Okay, so a lot of you also got this. So hanggang dito, okay, no? Most of you got that. Okay, now comes the more, I guess, no, the more unfamiliar territory for you. Okay. So now I draw my small signal model. Okay, let me draw my small signal model. For the transistor, this is my small signal model. No? I have G, I have S. Remember that my small signal model for the NMOS and the PMOS are exactly the same. Okay, so this is going to be VGS. This is an open circuit. Okay. Then I have a source here. This is GM, VGS. Okay. And then this is Rs of O. Okay. This is a common source, so this is grounded. No? A common source, your source is grounded. And this is now your drain. No? This is my source. So this is my transistor. This is my transistor. However, meron tayong isang component outside of the transistor. Ito. No? I have one component that is outside of the transistor. Where is this component? This component is connected from my drain to my ground. No? Itong R sub D. It's connected from my drain to the ground. So I have to draw that component also here. From the drain to the ground, R sub D. So ito lang yung transistor natin. Ito lang yung transistor natin. Ito yung isang component na nadagdag. Okay? Now what is GM? Now GM, we derive the formulas for that. That's 2 IDQ, okay, over V, okay. This is PMOS, no? This is PMOS. So instead of VGS, it's VSG Q minus the absolute value of VTH. No? You can derive this exactly the same way. If you get the partial of ID with respect to VSG, this is what is going to come out. So you derive it exactly the same way. And I just plug in the values of VSGQ, no? VSGQ and VTH. VSGQ is ito, no? 2.8. That's VSGQ, VTH, and IDQ. And I'm going to get here 1.281 millisiemens. Plug in lang, millisiemens. Now what about Rs of O? Rs of O is 1 plus lambda VDSQ over lambda IDQ. Yung sorry, ito na naman ako. VSD. Sorry. Even I make that mistake, no? VSDQ. over lambda IDQ. Okay, so plug in lang din. Ito yung VSDQ. Yung lambda is 0.1, yung IDQ is this. And this is going to give me 12.346 kilo ohms. So that's just by substitution. Okay, 12.346 kilo ohms. So ang sinasabi dito, okay, if VGS changes by, ano yun sa problem? 20 millivolts. No? If VGS changes by 20 millivolts, so that's a very small value. You can consider that to be small signal kasi 20 millivolts. Okay? So if this changes by 20 millivolts or VGS, V small g small s, pag small g small s, ibig sabihin change, no? Change in VGS is 20, ano magiging value nitong current source na to? Okay? So if VGS is equal to 20 millivolts, okay, GM VGS will be equal to what? No? That's 20 millivolts multiplied by 1.281 millisiemens. I don't know if I have that. Let me just compute that. That's 20 times 1.281. Okay, that will give me 25.62 microsiemens. No, sorry. Microamperes. Kasi millivolts multiplied by multi-Siemens is going to give me microamperes. Microamperes. Okay, so yan yung nagpo-flow dito, pababa. Saan magpo-flow yon? No? The current flowing here will just flow across the parallel combination of RO and RD. No? If I get the parallel combination of this, RO in parallel with RD, okay, I'll have to compute that again. Okay, that's 5 plus 12.346. That's 3.56K. That's going to be 3.56K. The parallel combination of RO and R sub D. So yung current dito, magpo-flow pa aketron, no? So let me just draw that, no? This is my output now. This is RO in parallel with R sub D. So what did I say that was? That was 3.56K. What did I say this current was? This current is 25.62 microamperes. Microamperes. So yung current na yan will flow this way. Right? It will just flow up there because this is an open circuit. So what will now be my output voltage? My output voltage is going to be, the polarity will be plus minus. It's going to be 25.62, okay, multiplied by 3.56. I'm going to get 91.21 millivolts. This is going to be 91.21 millivolts. So that's going to be my VSD, negative 91.21 millivolts. What is my gain? That's VSD, small subscripts, no? Over V no, sorry, this is VDS. Ito na naman ako. Kasi negative na eh, no? Sorry about that. This is VDS. Remember, this is D and S. Okay. VDS is negative 91.21, so my gain is VDS over VGS. So minus 91.21 millivolts divided by 20 millivolts. I'm going to get negative 4.56 volts per volt. Any questions? So again, the key here is yes, yung no, we're only computing for the change. No? You remember what I said before? You split the analysis into two parts. One part is computing for only the DC quantities, and the other part is only computing for the time varying quantities. No, so ginawa na natin yung DC part, no? We already computed for the DC part, and what I'm asking you here is only the change in output voltage if a change in input voltage of 20 millivolts is applied. No? So, meron tayong bias voltage. Ano yung bias voltage natin? 2.8 volts, no? That's VGSQ. So, ibig sabihin yung input natin umakyat above VGSQ by 20 millivolts. So, yun lang yung change. No? So, in the analysis, in small signal analysis, hindi na natin kino-consider yung DC quantities. It's only the time varying quantities. Am I confusing you more? Malabo ba? Anyway, try to digest that, no? Remember that basta't ang tatandaan nyo, we split the analysis into two. One is the DC and the other is the time varying. And we're only doing the time varying here. Wala na yung DC. Kung medyo nahihirapan ka to grasp at that, just think about it and then you can consult me also anytime. So again, the key here is, ito yung sa transistor. Okay, actually medyo advanced tayo ng konti because adding this component, which is external to the transistor, that's really the subject matter of the next module. No, but in the next module, it's not going to be a very simple circuit like this. No, you're probably going to have plenty other components because your biasing components, for example, if you use resistor divider biasing, papasok din yung mga components na yun dun sa model. Dito kasi, inassume ko lang na yung bias is already part of the input voltage, right? But in a real circuit, you have a biasing circuit that is used to establish the value of your source to gate or gate to source voltage. And that biasing circuit, papasok din dun sa yung mga components na yun, papasok din dito sa, idadagdag mo rin dun sa model ng transistor when you're computing for all of these values. So yun yung magiging topic, that's going to be the topic in the next module, and you're going to be doing that for all the different configurations. And then in the last module, you're going to consider now higher frequency. So pati yung mga capacitors ngayon, papasok na. And that's when you have to review your impedances because you're going to be dealing now with impedances. Okay, so that's all for today. Reminder, your midterm is going to be on Monday. It's going to start at 8 o'clock. It's a 2-hour exam. Okay, you don't have to bring anything except your pen and your calculator. No? You're going to be provided the paper that you use to do all of your computations. And the difficult to memorize formulas are going to be given to you, and also the constants are going to be given to you. No? Dapat yung mga ibang formulas dapat na nasa ulo na ninyo by this point. No? But the difficult to remember formulas will be given to you. So good luck in your exam on Monday. No, you just wait for announcements with regards to the room and all. Okay, I'll stick around till almost 2:30 in case anybody wants to consult. Thank you.